Hello. In the previous video, I have explained what is the confidence interval, and it was very brief. And summary, I'm not going to go over the summaries again. And here in this video, I'm going to talk about another issue which is interesting. Now we consider X is binary. The regressor we considered earlier was student to teacher ratio, which can take any integers, like non-negative integers. Like student to teacher ratio could be 1, could be 100, could be any number, any natural number. But now we are going to think about binary variable. So a random variable is called binary if the random variable takes only two values. And the two values are usually encoded as 1 and 0. The examples are, say, define a random variable x, which takes 1 if the class size is small and 0 if not. Or you can define x as 1 if female and 0 if male. Or you can think it as x equals to 1 if, say, vaccinated, or if you haven't treated, vaccinated, or if you are taking some drug, and 0 if not. So these are examples of binary regressors, and often they are called dummy variables because they are not actual numbers. They are dummies. Just I have information about class size and gender and your treatment, medical treatment record, but they are not numbers. So to include them in your regression model, we encode the outcomes as 1 or 0. So then it's clear that 1 doesn't mean there is no unit. So when I ask you, are you male or female? There is no unit. What is the, say, then the problem is, what is, say, when we say x increases by 1 unit, then y increases by beta 1. That's how we interpreted the regression model. But in this example, what is the 1 unit in male and female? Changing male to female, it means increase by 1. So from 0 to 1 is increased by 1. But it has no units. It has no meaning. So there is no, say, 2 or there is no 0.5. So 1 and 0 are just, it's on and off, like yes or no type questions. So the interpretation, so the mechanism, the mechanics, the estimation procedures, everything is the same, but the interpretation has to be different. We are going to talk about this. So as I said, the beta 1 was interpreted as the slope, but now it does not make sense. And also find that here in this example, I assigned 1 to women and 0 to men. But it does not matter if I assign 1 to man and 0 to female, right? Changing 1 and 0 does not cause any problem. And if you want to make it more like strange, then instead of 0, say assign 1 to women and assign 2 to men. That causes no problem. So what you need to do here is you just need to distinguish from the data. You just need to distinguish women from men. No matter what, you just assign different numbers for women and men. That's all. It doesn't matter what number you are using. So of course we are using 0 and 1 because they are the simplest, easiest numbers to handle. But as I said, but they don't have any numerical meaning. They are not numbers, right? Then how do we interpret? Now we have only two values in x, so simply you can make cases, so split cases and think case by case. Suppose that when x equals to 0, which means small class size, so if you plug in 0 here, this term beta 1x will disappear. This term will disappear, and then as a result, you only have y equals to beta 0 plus error term. And which also means that the error is expectedly 0. The expected value of error is 0. Then the expectation of y is simply beta 0. So beta 0. Then as a result, now the intercept beta 0 has its interpretation. Beta 0 must be interpreted as the expected outcome when x equals to 0, right? The conditional expectation of y given x equals to 0 is beta 0, right? And do the same thing for the other case. When x equals to 1, plug 1 into here, so x is replaced by 1, then y, the equation becomes beta 0 plus beta 1 plus u. Then again, u has mean 0, expectation is 0, so the expectation of the outcome given x equals to 1 is simply beta 0 plus beta 1. X was replaced by 1. So then now you can interpret beta 1 based on these two definitions. So beta 1 is the difference between these two conditional expectations. So then you can interpret beta 1 as the difference in group-wise means, group-wise expectations. So group-wise, x1 is one group, x0 is another group. So a population difference in group means. That's how we interpret. So we don't say beta 1 was interpreted as the slope, but as I said here, slope interpretation is not appropriate. It's not, technically it's not wrong, but a better interpretation is using the difference. And you think about the example that we considered. So originally we used student to teacher ratio as itself, as it is, but instead of using the student to teacher ratio data variable, I am going to classify the observations into two groups. One is a group that has smaller class size, less than or equal to 20, and the other group is student to teacher ratio strictly greater than 20. So 1 is assigned to small, 0 is assigned to large. And use D is 1 or 0. Use D in the regression model instead of X. Everything is the same. Everything is the same. Stata calculates the results in the same way, and now you know how the result is reported in this way. Now you understand what it means. And if you don't want to use the regression model, actually the same thing can be done if you use this. Simply classify the observations. So you have one large data and divide the data into small class size group and large class size group. And for each data, you can calculate the average and the standard deviation and count the sample size. Do the same thing for the other data, and you get this. And based on them, you can calculate the same results as you got here. And remember, the intercept beta 0 is the conditional expectation of 0 group, right? Which is exactly here. And beta 1 is the difference, which is exactly shown in this table. And standard error is calculated according to this formula. If you have learned how to calculate standard error of the difference of two groups. If you have not learned it, I did not teach this in my 320 course, so I don't think it's important. But anyhow, what you are doing in the regression is actually the same thing as calculating mean and standard deviation, which is easier to understand. Okay, and I added some slides because when you have binary data, when you have binary data, the scatter plot is usually a little bit different from the typical scatter plot you see from the textbook, because the only observations are either 0 or 1. So there are a bunch of observations aligned exactly at 0 and exactly at 1. So the data can be perfectly divided into 0 group and 1 group. That's the definition of binary variable. And in this case, if you see this scatter plot, you may still imagine a slope going through a regression line, going through those data. It is not wrong. It is okay. It is okay to make a line like this, and this is how Stata calculates the parameters, estimates the parameters. However, this interpretation is not desirable because, as I said, 0 and 1 has no meaning. So distance between 0 and 1 could be larger, could be smaller. There is no meaning, and like it could be any other number as long as they are different. So, and when you change the scale and the location of those 2 points, the slope will change. Like when you widen this, slope will be more flatter, and when you narrow down, then slope will be more steep. Anyhow, slope is not how we interpret this, but this is how you have to interpret. You just think that, like, you can imagine there is a average of those this group, average of those observations is this point, which is here, and average of one small class size group is here. Then the difference is what you get. And so there is no meaning about the difference between 0 and 1. Like those difference is just vertical difference, and horizontal difference plays no role. The horizontal difference has no meaning. That's the point in interpreting a binary regressor case. Okay, simple summary. Anyhow, in the end, at the end of the day, if you don't understand what it is, you can forget about this, because everything else is the same. Just at the last step, when you estimate the parameter, the regression model from Stata, and even if you interpret the results in the same way, that is not wrong, but just it is not the best. The best way to interpret that is using difference. Okay, this is it, and see you in the next lecture. In the next lecture, we are going to see a more complicated topic. Can you read it? Heteroscedasticity, homoscedasticity. We are going to talk about this. It's a very it's maybe the most difficult term to pronounce in any economics course, I guess. So see you in the next lecture.